In this video, I'll be going over the answer key for Friday, April 3rd. In our topic today are titrations. A titration is when you mix an acid and a base and you monitor the pH change, either with a pH meter or some kind of indicator. And you're usually doing this because you have an acid and you don't know what the concentration is and you want to figure that out systematically. So all the questions in this problem set are all titration questions. So I'm going to do question 1 and then let you do practice with 2, 3, and 4. Now, the way you do a titration really depends if you have a strong acid or a weak acid, or it could be a strong base or a weak base. So the way I broke down question 1 is I'm going to show you how to answer all of these questions with your strong acid of HCl. Then I'm going to show you how to answer those questions with your weak acid of hydrofluoric acid. So first, strong acid. I have a 25 ml sample of 0.1 molar HCl. What is the initial pH? Well, the definition of a strong acid is that it breaks down 100%. So if I have 0.100 molar HCl, that's 0.100 molar H+. pH is minus log H+. So pH is minus log 0.1, so my pH is 1. What is the volume of added base at the equivalency point for each titration? So my base is 0.2 molar potassium hydroxide. So the first thing you should do is write a balanced equation. Potassium hydroxide plus HCl makes water and potassium chloride. Then it is just a mole to mole problem. You're just doing chemistry like we learned in Gen Chem 1. So I start with 0.100 mole HCl in 1 liter, or 1 molar. So instead of having it in liters, I'm going to go to milliliters. So for 1 liter, there's 1,000 milliliters. And the reason I'm doing this is because I want to know how many moles of hydrochloric acid I have. And I added 25 milliliters. So now my units are 0.100 molar HCl divided by 1,000 milliliters of HCl. I use 25 milliliters, so I multiply that by 25 milliliters. Milliliters cancel out. And the number of moles of HCl I have are 0.0025. Alright, so now I can figure out how many milliliters or liters of NaOH I need, so I can take this HCl and neutralize it. That's what the equivalency point is. The amount of acid and base are the same. So looking at my equation, potassium hydroxide and HCl react in a 1-to-1 or 1 mole to 1 mole manner. Their stoichiometry is 1 mole to 1 mole. So if I have 0.0025 moles of HCl, for every 1 mole of HCl, I need 1 mole of, I accidentally wrote sodium hydroxide, that should be potassium hydroxide to interact with HCl. Now, from my problem, I see, well, I have 0.200 moles of potassium hydroxide for every 1 liter of potassium hydroxide, because that's what molar stands for, again, moles divided by liters. So let's follow our units. Moles of HCl cancel out. We're left in moles, again, potassium hydroxide. Moles of potassium hydroxide cancel out. We're left in liters of potassium hydroxide. So to neutralize this acid, you need 12.5 milliliters of potassium hydroxide. 3. What's the pH at the equivalency point? When you mix a strong acid and strong base, let's go back to the equation, you're making water and potassium chloride. That potassium chloride is not an acid or a base, so you just have water, and at 25 C, the pH of neutral water is 7. D. What's the pH of after adding 5 mils of your base at the equivalency point? So we're at the equivalency point, then we go 5 mils of base over. So let's kind of look at our reaction. So we had water and potassium chloride, And again, I keep writing NaOH. That's the base you normally use. But we add more potassium chloride. And we're going to do this because the reason why I wrote this out is to show you what we're going to have in solution is OH minus. So we're going to make hydroxide. So let's see how many moles of potassium hydroxide we have. So we have 0.200 mole potassium hydroxide for every 1 liter of potassium hydroxide. Again, I'm going to change that to milliliters because I added 5 milliliters and I want to figure out moles. So we have 0.001 moles of potassium hydroxide because we started with 0.2 molar and only added 5 mils of that. Well, I want to know what is the molarity of my excess OH, because I know how many moles it is. It's 0.001, but molarity is moles divided by liters. So I need to look at my total volume in my titration so far. So I started with 25 milliliters of HCl. To get to the equivalency point, which we looked at in B, I needed to add 12.5 milliliters of potassium hydroxide. And in D, I add 5 milliliters more, which means my total volume is 42.5 milliliters or 0.0425 liters. So my molarity of hydroxide is 0.001 divided by 0.0425, which is 0.0235 molar. This is the concentration of OH minus after adding 5 mils after the equivalency point. So I can figure out the POH from that. POH equals minus log OH. So my POH is 1.63. Then I can figure out the pH because pH plus POH is 14. I just figured out POH, so pH is 12.37. Lastly, draw a titration curve. So based on what we just talked about, you're at very low pH at the equivalency point, which is 12.5. You're at 7. Then once you go past the equivalency point, you're at a very high pH. Right. So let's now look at how this is different for a weak acid. And since we have a weak acid, not all of that breaks down. So initially, we have to figure out, okay, how much HF has broken down to H3O+. So we need to do an ice table because we're working with a weak acid. And we've already seen problems like this before. So we have hydrofluoric acid plus water goes to H3O plus F minus. Our Ka is F minus multiplied by H3O divided by HF. That's equal to our Ka value. 6.6 times 10 to the minus 4. So we only have products to start with, so minus x, and plus x. Again, water's a liquid, so we don't care about it. So we have 0.100 minus x, and x. We look at our starting value compared to our Ka, and our starting value is 100 times bigger than our Ka, so we can say minus x is negligible. So 6.6 times 10 to the minus 4, which is Ka, equals x times x divided by 0.1. Multiply 0.1 on each side. 6.6 times 10 to the minus 5 equals x squared. Takes the square root of each side. X is 0.00812. Since that's x, that's the amount of H3O+ we have. From there we can find pH, because pH is minus log H+. So pH is 2.09. B is actually the same. So in a weak and strong acid, as long as the mole equivalency is 1:1 in both cases, or 2:2, or as long as your weak acid and strong acid have the same stoichiometry to your base, the calculation is the same exact thing. C is where it gets kind of tricky here. So what's the pH at the equivalency point? Alright, so if we add enough base to our HF, all of that HF is going to be converted to F minus. F minus is a weak base, so it's going to act like a base and create OH minus. So this is how you should work through it. First, Initially, how many moles of HF did we start with? Well, it was 0.1 molar. We added 25 milliliters. That's 0.0025 moles of HF. At the equivalency point, all that HF is now F minus, so the moles of F minus that we have in solution are 0.0025. I want molarity though, so let's look at molarity. So we started with 25 milliliters of HF. We added 12.5 milliliters of potassium hydroxide, so the volume is 37.5. So molarity of F minus is 0.0025 divided by 0.0375 liters. Remember, it's moles divided by liters, which is 0.0667. So that's my molarity of my weak base. And so base with water, F minus plus H2O, the base will take the hydrogen from water to make HF and create OH minus. So minus X plus X plus X, so our equivalency point. Now we need to figure out what Kb is. So our relationship for any buffer or conjugate pair is that Ka times Kb equals Kw. And at 25C, Kw is 1.0 times 10 to the minus 14. So we know the Ka, 6.6 times 10 to the minus 4. Now we have to find the base dissociation constant Kb. And so we take Kw divided by Ka, that is equal to Kb, which is 1.52 times 10 to the minus 11. From our equation here, we can get Kb equals HF multiplied by OH minus divided by F minus. Start filling in our values, and since we know the value of Kb, we know that minus X is negligible. So 1.52 times 10 to the minus 11 equals X times X divided by 0.0667, or 1.01 times 10 to the minus 12 equals X squared. And when you take the square root of that, you'll find X is 1.01 times 10 to the minus 6. That is our OH. And then from there, we solve for POH, and it looks like my paper got cut off here, but I can just talk you through it. So once we figure POH from doing this calculation, we can figure out pH by pH plus POH equals 14, and your pH should be, if I remember right, roughly 8. So when you're at the equivalency point and you started with a weak acid, you will now have a weak base. So you need to do a weak base calculation to figure out the pH. What's the pH after adding 5 mils of base past the equivalency point? It's the same as in the strong acid because you have nothing but base. So adding in this strong base will completely dominate any OH that your weak base has made. So we don't even have to care about the weak base anymore. We only care about the strong base. In E, here's my curve. So at a pH of 8, we're at the equivalency point, so that's 12.5. We're at low pHs before the equivalency point and high pHs after the equivalency point. So, like I said, there's 3 other titration problems. Try those. If you have questions with those, please do let me know. Otherwise, I will see you in the next video.